So this week and last week we've been practicing the Hasse diagram. I'm going to go over a little bit more on video to show how this can be used to help us think about power analyses using mixed models. So the Hasse diagrams we've been doing in class up to now did not include super and subscripts on each of the nodes. The superscript and subscripts we're going to add today, and they indicate, well, the superscript indicates the number of different levels of that effect. So, highly related to degree of freedom, of course. The subscript indicates the degrees of freedom. So this helps us think about how we should be constructing our expected mean squares also, because that can be a little bit difficult, and we're going to talk a little bit more about that in this set of notes. So let's say A has 5 levels, B has 4, C has 2, and we have 2 replication of every ABC combination here. So let's look at our simplest case possible here. This would be, well, maybe not simplest. This is probably a fully nested design would be simplest, but the case with only A and B to begin. So we've got the number of levels, degree of freedom. Levels, degree of freedom. Levels, which is 5 times 4 here, which gives you 20, times degree of freedom, which is 12, the 4 times the 3. And then we've got our levels, which is 2 times 20, because we had 2 replications for all 20 treatment combinations. And then 20 degrees of freedom for the error. Of course, that is 5 times 4 times 1, because 2 minus 1 is the term for replications. So that's pretty clear, I think. Here, remember, because we have the parentheses around B, this would be considered random. A is fixed, so everything below it is random. Now let's consider this case here. Let's first identify our terms. A is random, 5 levels. B is random, 4 levels. C is fixed, 2 levels. So this might be something like our, this could certainly relate to our project data. Depending on how you choose your random and fixed effects, I'm not saying anything, but we do have a fixed effect with some randoms here, and that might be something like what you consider. Make sure you understand all these degrees of freedom. I won't go through each of these calculations, maybe just show you the first. A times B, you have 5 times 4 gives you 20. Well, I already showed you that one. Let's try this one, AC. 5 times 2 gives you 10, 4 times 1 gives you 4, and so it's pretty self-explanatory, I think. Finally, the fully nested. Notice how we just add to the degrees of freedom by the factor of the number of levels added for each of these. Cheese raters. This one was our one we worked through and had a little difficulty working through the model and thinking it through. Let's add our degrees of freedom now to the Hasse diagram. Maybe this will illuminate things a little bit more. So we had our background, which had 2 levels, urban and rural. And then the cheese type, which was 4 levels. And then we had a random effect of the respondent. And remember, we had 10 respondents from each of the backgrounds, of which there were 2 levels. So let's make sure we understand all these numbers here. We had 2 levels for background, 4 levels for cheese, 20 for raters, because we had 2 times 10, 10 raters for each background. Then we're able to cross the background with the cheese type, which will give us 8 and 3 for our super and subscripts. And then we can also look at the effect, the random effect. This, by the way, is fixed, notice, because those are both fixed factors, B and C. But the interaction effect between the rater and cheese type, this would account for random variation in cheese preference by respondent, so individual liking or dislike of different kinds of cheeses. This would be the 20 times 4 for the number of raters times the number of cheese types, and of course 54 for your degrees of freedom. And finally we get to the error, which this is because we had 2 of each cheese replicated, and remember it was in random order, so they didn't really know which cheese they were getting for any of the 8 cheese bites they got to taste. Okay, this is, I'm going to skip over this. This is in the notes. We did this in class. I don't want to point out anything on here except to show you point number 4. The unrestricted model assumptions, the EMS for a term that's contributed will include all random effects below it. So we talked about doing both in class, and I just didn't want to get into the whole restriction, non-restricted, or unrestricted model business at the time. But I think I went by in class last week what I had been taught. I'm going to go by what R does now. And so from now on, we're going to assume this unrestricted model, which also is what Gary's doing. So I'm going to kind of change tune a little bit. Be aware that sometimes we will do the restricted, but unless I tell you to do restricted, we'll assume unrestricted from this point on. So let's make sure this is what we spent a lot of time in class on, because I think it's really important that you understand this. A is fixed, B is random here. We have cross terms. We went through all of this in class, so just make sure that you can match what's here on each of these sheets to what we did in class. I think it's better for you to work it out than to just look at the results here, because you're not going to really fully grasp what's happening here without working it out yourself. I firmly believe that. And so here's all of our effects for the three-way model. Again, we did all of this in class. Do notice here, let's pick on A here. A is a random effect. We have the, of course, random effect associated with A, but all the lower order terms too, which in class I think we did include these. If it had been restricted, we would have excluded those. If we have the nesting, of course, we talked about in class how that affects the interactions, because we have no interactions. That's what tripped us up, if you recall, on the cheese tasting experiment. Everybody wanted to put in the interactions, but having interactions or crossed effects doesn't make sense when there's nesting. So our cheese raters, you can go back and check all this. All right. Okay. Here he goes back to chapter 7 material and talks again about the approximate F tests. I'm gonna again kind of skip this because we brought it up in chapter 7 just like Gary, but he brings it back up again here. I'm gonna skip all of this. He finally gets us to this last design where we had the three-way interactions. Let's see, this one. Sorry, I'm clicking all over the place. It's difficult. He talks about how it's difficult to define the tests for these. We worked through that in class, okay? This is our approximate F test handout that we did. But what I want to talk about is using the Hasse diagrams here, because we worked it out in theory without the Hasse diagrams, which I think is really essential to do first. But let's go back and look at that Hasse diagram. Gary mentions that the denominator for the term using the unrestricted model assumptions is the first random term below the term of interest. So let's go back to that model here. Okay, so the first random term below your model term of interest. We have a lot of slides to click through. Okay, so this one here in the middle. So if we want to, for example, think about effect A, our random terms directly below A are going to be AB, AC, and BC. So which random term do you use? It may not be obvious to you, and it shouldn't be. This is a case where we know we need to come up with an approximate F test. So your Hasse diagram is really nice for this because it really shows you what your effect term should be clearly, except in the case when it's not clear and you have to use an approximation like we've been practicing in class. So this is Another reason I like to show the Hasse diagrams after, because you already know the solution at this point, and the Hasse diagrams just point out that approximate F tests are needed for effect A, B, and C. Now, are they needed for the lower order effects? Well, let's start at the bottom. The random effect directly below our interaction term for ABC is error. There's only one. So we know that we can construct an F test using this MSE, or MSABC, divided by MSE. Similarly here, for AB, AC, BC, there's only one random term following those terms. So if we test AB, we divide by ABC, the mean square for ABC. If we test AC, also divide by that. So it's really, I think these are really helpful for understanding when you need to construct an approximate F test and when you don't need to go to that trouble. The computational method that we used in class, or the more algorithmic method we use for constructing these F tests, are still needed though. This just, knowing that I can't exactly test A here just tells me to go use that approximate F test method, but it doesn't really illuminate how I should construct, I don't think. Maybe one of you thinks it does, and that's great if you do. Notice with nesting, there's no issue. It's easy. It's only when we get all this crossing with random and mixed and whatnot terms. Okay, so in the next set we'll talk about power.